We are done with the nature of mathematics. Now let's proceed to the question, what is mathematics? The book outlines 4 definitions of mathematics, but accordingly, mathematics has no universally accepted definition. Tobey's 2012. Again, mathematics has no universally accepted definition. We will just quote some definitions that are proposed by famous mathematicians. Some definitions of mathematics are: first, mathematics is the science of quantity, and that is from Aristotle, 384 to 322 BCE. Another definition is it is the science of indirect measurement by Augusto Comte from 1798 to 1857. The third is mathematics is a science that draws necessary conclusions by Benjamin Peirce of 1809 to 1880. And lastly, Bertrand Russell from 1872 to 1970 says that all mathematics is symbolic logic. Please don't forget these people. Our definition of mathematics is one which we base on the experience many students might have about mathematics, and experienced teachers had while shepherding them in their mathematics education. Mathematics has 2 essential characteristics. How many? 2. What are these 2 essential characteristics? First, it is a form of language. Again, the 2 essential characteristics of mathematics is 1, a form of language, and second, it is a body of knowledge. As language, we use it to name and describe objects or events that reveal quantity, form, pattern, and change. As a body of knowledge, it is a set of concepts and relations among concepts whose properties and characteristics are obtained through logical reasoning. So from this slide, you have some definitions of mathematics and the 2 essential characteristics of mathematics, which are it is a form of language and it is a body of knowledge. Now, let's proceed to mathematics and patterns. On top of the early humans' need to describe quantity, they also need a language to describe and predict patterns in nature. The Ishango bone, for example, was an early mathematical exercise to count the cycle of lunar phases as they relate to menstrual cycle of adult women. What reasons compelled ancient people of Ishango to track the menstruation cycle? We cannot ever answer this with complete satisfaction, but we can make intelligent guesses based on our present observations of people's cultural beliefs about menstruation. In the United States and United Kingdom, for example, women during their period are observed to be irritable, and so it pays never to cross them during their period. Bears roaming the temperate forests of these places have a keen nose for blood, and so it is prudent for women never to enter the forest during menstruation. In Poland, to have sex with a woman in her period is sure to kill the man. In the Philippines, women are advised never to take a bath because taking a bath during one's period causes infertility. The ancient people of Ishango probably have more strange beliefs about menstruation, possibly even stranger than our superstitions, and so it pays to track in the menstruation cycle of women. There are frequently observed patterns in nature and the world. Let's begin with a honeycomb. A honeycomb is nest built by bees. It is made from beeswax and is composed of cells in the shape of hexagon, sometimes pentagon or heptagon. A honeycomb is the nest of honeybees, and bees collect nectar from flowers and deposit them in honeycombs made from beeswax, a substance also derived from honey. Roman scholar Varro, from 1st century BCE, suggested in his book De Agricultura, on agriculture, that the propensity of honeybees to build homes as a tessellation of hexagons may have to do with the possibility of a hexagon inscribed in a circle is the polygon that encloses the largest amount of space. The link between the unique shape of honeycombs and the mathematical property of hexagons was formally stated by Pappus of Alexandria, the last ancient Greek mathematician. Pappus pointed out that triangles, squares, and hexagons are the three regular polygons that can tile a plane without gaps. For choosing the design of hexagons, honeybees seemed imbued with natural wisdom because it is the polygon which holds the largest quantity of honey given a limited amount of beeswax. In the figure, cells of honeycombs in the shape of hexagons allow bees to store the largest quantity of honey given a limited amount of beeswax. And this figure shows that shapes are made of hexagons 1, 2, 3, 4, 5, 6. And to emphasize, tessellations is just moving up, down, rightward, or leftward of a shape to form a series of interconnected shapes. So that is tessellations in geometry. So what it says, hexagon is the best shape to allow bees to store the largest quantity of honey. And who teach them that? Isn't it the creator? Okay, so I think even these insects were designed by God to teach people a lesson. Okay, so they followed a certain rule of shape where they can store large amount of of honey, even if they have limited beeswax. We call the process optimization. We can find this in mathematical investigation. So optimization is a field of mathematical investigation used to aid decision making in business and industrial engineering. The goal of optimization is to maximize or minimize the quantity of an output while at the same time minimizing the quantity of resources needed to produce it. So in relation to making honeycombs, the bees apply the concept of optimization. That is, to maximize or minimize the quantity of an output while at the same time minimizing the quantity of resources needed to produce it. So what resources the bees need to create honey? Okay, so they need what? Nectar. So even if they have small amount of beeswax, they can still produce much or hexagon. The honeycomb, which is in the shape of a hexagon, can hold more honey rather than of that other shapes. Next, the snowflake. We are still in the frequently observed patterns in nature and the world. Second is the snowflake. Description: a feathery snow crystal which nucleated from dust particles suspended in the atmosphere. Molecules in ice crystals join to form hexagonal structure, which is then repeated as the crystal accumulate more crystals and grow in size. In freezing temperatures, water molecules in the atmosphere organize themselves around suspended dust particles to form snowflakes. Again, water molecules in the atmosphere organize themselves around suspended dust particle. Look how amazing snowflakes are made. Water molecules suspended themselves around dust particles and they create into crystals. Not two snowflakes are exactly alike, however, but they always display a stunning symmetry. In 1611, Johannes Kepler, the mathematician who first gave us the laws of planetary motion, was curious why snowflakes often display a six-fold symmetry. Who was the person? Johannes Kepler. Who was Johannes Kepler? The mathematician who first gave us the laws of planetary motion. And when this happened? 1611. In the figure, we can say that snowflakes are an examples of fractals. What are fractals? Fractals are objects whose smaller parts look similar to the bigger part. The general shape of snowflakes, for example, a hexagon, but when magnified under a magnifying glass, its smaller parts look like tiny reproductions of the entire snowflake. This repetition of shape at the minuscule level is called self-similarity. Okay, so fractals are objects whose smaller parts look similar to the bigger part. But when we say self-similarity, this is the repetition of shape at the minuscule level. Computer programmers use fractals to generate the in-game environment of many computer games. Mountains, deserts, and forests, for example, display self-similarity. A lump of soil, when magnified under a microscope, reveals a landscape which looks pretty much like the landscape of a desert. As a result, it is more cost-efficient to simply generate images of various landscapes using fractals than paint them individually by employing the skills of artists. And I also remember one of the movies long time ago, maybe you did not catch up with this. You were not able to catch up with this movie. Maybe it was on my time. Remember Lord of the Rings. This movie needs plenty of people. Do you think they would hire as many people as it needed during that time in order to produce a more realistic picture of the vast or the multitude of people who should be in that one place at a time? No, they will not, given the resources to them, maybe. But what did they do? It's the process of self-similarity, displaying self-similarity. So objects in nature which display self-similarity are lightning, root system of plants, veins and nerve system of the human body, ferns, mountains, clouds, and more. In relation to the characteristic that is shown by snowflakes, we have what we call recursion formula. Accordingly, a mathematical statement or statements that repeat a process to produce a list of output with an identical or shared property is called a recursion formula. In an algorithm, this is done by a do loop structure. So, computer science students, you will meet recursion formula and do loop structure. The formula to generate the elements of an arithmetic or geometric sequence is an example of a recursion formula. So in translating recursion formula to a computer science code or program, this code do loop structure can generate a sequence of like 1 2 3 4 5 6 7, and depending on the terminal variable value of the variable that you will set. So it works like you set a variable into something like example 2, and then you want to end it to 10. So you just make a do loop structure where codes composed of the initial value 2 and the ending value of the variable is 10, and it will just continue on looping until it reach 10. So that's a recursion formula. So see, the manifestations that it occur in nature can be used in now more advanced technology in our society, including the microchips and other computer systems and operations. So that's recursion formula. So from nature, we learn from nature and then we apply it to make our lives better. But do we really make our lives better out of these innovations and inventions? Those were things to be discussed in maybe next topics. The next to the frequently observed patterns in nature and the world is the tiger stripes. Sorry, there is a clerical error. Tiger stripes. The stripes on the tiger are in general evenly spaced and perpendicular to the spine. The stripes help with camouflage. They allow the tiger to blend with its environment. Again, this is natural patterns in our world. The stripes of tigers and zebras, the spots on hyenas and other colorations and patterns displayed by skins of animals show a regular pattern which is easily recognized by people. Why they came to acquire and inherit this biological trait rests largely on the survival and reproductive advantage it gives to animals. For one, stripes and spots help with camouflage. They render organisms unrecognizable from the surrounding environment, which is interestingly is a strategy to adopt by both prey and predators. For zebras, the alternating stripes of white and black help control body heat, since black absorbs heat and white reflects it. The resulting temperature differences initiate a movement of masses of air around the zebra's body, which helps in managing body temperature. The, stri- the striking regularity in pattern and distribution of coloration on animal skin got one mathematician so interested he proposed a mathematical theory for this phenomenon. Alan Turing, also famous in the computer world. Alan Turing, the famous mathematician credited for breaking the Nazi Enigma code in World War II, proposed that two substances were behind this pattern. He called them morphogens, the two substances which are behind the patterns of the natural animal skin discoloration. We have also Turing machine in the computer world. Okay, so the two substances which were behind the pattern, we call them, or he called them, morphogens. How morphogens work? These morphogens reacted with each other and diffused through the embryo according to a system of equations, which he called reaction diffusion equations. One morphogen activated the manifestation of a stripe color, the other inhibit it. So, what can you say about that? These colors of the animals were not accidentally made. They are designed for something. First, for one, it is to camouflage. Another, for the zebras, to um, regulate the heat, manage the temperature of the body. Our Creator God was or is an amazing God. And if He did this to the animals, what more did He do for us humans? It's interesting, isn't it? I'm sure you like to discover what's in you more than what's in these animals. Let's continue with hyena spots. The spots on hyenas are shaped and distributed in a pattern that helps also with camouflage, as what was discussed earlier. The sunflower. A sunflower displays many patterns. The most prominent among them are intersecting families of spirals. If you take a closer look of this sunflower, you will notice spirals in it. Okay, spiral, spiral. Many patterns can be observed in a sunflower. The distribution of seeds on its face spirals in clockwise and counterclockwise directions. The seed starts at the center and extends outward to the petals, with each seed placed at an angle from the neighboring seeds, producing a spiral configuration. Just precisely what is that angle? It is 137.5 degrees. The angle has to be so precise such that a deviation of 1 over 10 of a degree will not produce the two families of spirals displayed in a sunflower. This angle is called the golden angle and is the angular manifestation of the golden ratio. What do you think about sunflower? Just take note of the deviation of 1 over 10. That's 0.01. And it's just so tiny when you think it. But if the growth of seeds deviated with just at least that certain amount of degree, it will not form a perfect spiral. Okay? The nature shows how magnificent, how brilliant, how awesome, how amazing, how wonderful our God is. The one who created this nature, the patterns in nature. Again, they are not just accidentally made, but they are carefully crafted to serve for a purpose. How about us, humans? Next, in line with the patterns in sunflower, we will be dealing with Fibonacci sequence or f of n. The Fibonacci sequence or the Fibonacci numbers and the golden ratio will be discussed on a separate part of this presentation. Fibonacci sequence is a list of ordered natural numbers 1, 1, 2, 3, 5, 8, 13, 21, 34, etc. Notice the relationship. The first two are 1 and 1, and the succeeding natural numbers are the sum of the two consecutive numbers immediately preceding them. So it's just so easy to continue writing the Fibonacci sequence. Let's begin with 2 ones, and the rest will be the sum of the succeeding consecutive numbers. So how does it work? 1 plus 1 equals 2. 1 plus 2 equals 3. Let me use the pointer. 1 plus 1 equals 2. 1 plus 2 equals 3, 2 plus 3 equals 5, 3 plus 5 equals 8, 5 plus 8, 13, 8 plus 13 equals 21, 13 plus 21 is 34, 21 plus 34 is 55. What comes next? You just simply add 34 and 55 and you get 89. So that's how Fibonacci sequence work. So where can we apply this? Okay, I will leave that question here, but we will deal with that later. We also have golden ratio. The ratio f of n over f of n minus 1 of two consecutive Fibonacci numbers approaches the value of 1.618 as n becomes infinitely large. This ratio is called the golden ratio, which is an irrational number. The golden ratio is also called by other names. We have golden mean, golden proportion, golden cut, divine section, divine proportion, extreme and mean ratio, and medial section. Let's proceed with the snail shell. Another interesting patterns in nature and the world that we can observe is the snail shell. The snail shell has the shape of a spiral. The radius of the shell increases in length as the mollusk grows inside the shell. The shell of snails grows as the soft, fragile body of the mollusk inside the shell matures. Its outward growth has an uncanny resemblance to a spiral. Two geometric patterns are at play in their shells. First, the spiral, which also resembles the distribution of seeds in a sunflower, and second, the fractals. Okay, two geometric patterns that play in the snail shell. First, the spiral that resembles the distribution of seeds in a sunflower, and the second, the fractals that works in the snowflakes. The shell's configuration is self-repeating. It repeats its structure as the shell grows in size. In addition, the spiral of the shell traces the opposite corners of the squares generated by Fibonacci sequence. The spiral shape of the shell of snails also resembles the configuration of many galaxies. The Fibonacci sequence and the golden ratio are observed in many living things, in artistic design, in the behavior of people in relation to stock prices, Stocks 2016, and in the moral development of an individual person, Rose 1992, to name a few. One wonders of evolution is at play here. Is there something about this sequence which gives plants, animals, and humans a better change at survival and reproduction? Okay, so is there something about this sequence which gives plants, animals, and humans a better chance at survival and reproduction? Let's find out when we deal with Fibonacci sequence and golden ratio. We have also what we call the Elliott wave principle. Elliott wave principle proposes that the sequence of highs and lows in the behavior of stock prices mimics the propagation of a Fibonacci sequence. So that is the Elliott wave principle. The weather patterns. One of the frequently observed patterns in nature and the world. Weather is observed to repeat a pattern for days, weeks, or months after which a new weather sets in. This sequence of weather patterns produces a cycle such as dry monsoon seasons, summer, autumn, interspring seasons, habagat-amihan, wind patterns, etc. Weather is attended by many patterns. The first pattern early humans came to see is the cycle of night and day. The sun is seen in the sky 12 hours on average and disappears for the next 12 hours before it appears again. Seasons also follow a cycle. In the Philippines, the changing seasons are marked by a change in wind direction and quantity of rainfall. Amihan describes the cold mass of air coming from the northeast. It is accompanied by low temperatures, little rainfall, and a prevailing wind from the east or northeast. That is amihan. Habagat, on the other hand, is characterized by hot and humid weather, frequent rain, and a prevailing wind coming from the west or kanluran or southwest Timog Kanluran. Amihan begins sometimes between November and December and ends sometime between May or June, 6 to 7 months on average. Habagat begins June and ends close to October. On average, the beginning of a particular season begins every after 365 days. How can we describe this pattern mathematically? Is it possible? How do we put in mathematical language the statement, the season is habagat from June to October and amihan for the rest of the year? Let's find out in the example given in the next slide. Example 1.1, mathematical language to describe seasons. Write a mathematical sentence to describe the season as a function of month of the year. Solution. Make the following assignments. 1 equals January, 2 equals February, 3 equals to March, 4 equals to April, 5 equals to May, 6 equals to June, 7 equals to July, 8 equals August, 9 equals September, 10 equals October, 11 equals November, and 12 is equal to December. For the seasons, let 1 equals amihan and 0 equals habagat. Season is a function of month. Thus, if y stands for the season and x the month of the year, then y is equal to the f of x. And we define the function in the following manner. F of x equals 1 if x is equal to 1, 2, 3, 4, 5, 11, and 12. 0 if x is equal to 6, 7, 8, 9, or 10. So when we say 1, amihan, and 1 to 12 represents the different months of the year. So this function, I'm sure you have experienced writing one in your senior high. I was a teacher in general mathematics before and pre-calculus in the senior high, and I'm sure you have passed piecewise function. General mathematics is real across all senior high strands. So you know what's a piecewise function. But if in case you have not known piecewise function, this is how the piecewise function looks like. It is also called conditional function because 1 if it's true here, 0 if it's true here. Okay, so that's a piecewise function, also known conditional function. Flowers' petals still frequently observe patterns in nature and the world. The number of petals of a flower are observed to follow the following pattern: 3, 5, 8, 13, which are numbers found in Fibonacci sequence. And in many flowers, the petals display the distribution of the Fibonacci sequence. The number of flower petals often observed in nature are 3, 5, 8, 13, 21, 34, 55, and 89. If you notice in this example, we have 1, 2, 3, 5, 8, 13, 21, and 34. So there is still the pattern that we can see in this natural thing, which are the flowers. Next is human populations. The demographic distribution of people in human populations is observed to follow a pattern. Poor nations display a pyramid-shaped demography with the young occupying a prominently large section of the population, but as a nation progresses economically, the base thins out in favor of the older segments of the population. But once a nation progresses economically, the base thins out in favor of the older segments of the population. Most people ask this question: why is it that couples who are relatively well off bring forth fewer children than couples who come from lower economic classes? Is that your observation also? The difference is staggering and is the frequent point of discussion in demography. Those who belong to A-B class raise 2 to 3 children on average, but those in the lower class raise 5. Philippine Commission on Women 2014. The pattern here is one between income and number of children, or income and family size. This pattern is also replicated at the national level. Philippines, for example, has been improving in economic standing for 3 decades as measured in GDP growth rate, but that is accompanied by a declining fertility rate. GDP in 1961 was 5.6% and stood at 6.9% in 2016. In that same period, fertility rate declined from approximately 7 births per woman or woman to 3 births. A similar trend is observed in other countries as well, notably in Japan, Korea, and Singapore. Our observations of income, be it family income or national income, and rate of population growth, family size or national population size, is one of inverse proportionality. Again, inverse proportionality. What does it mean? As income increases, rate of population growth decreases. In mathematical language, this is written as P P sub R, where PR is the rate of population growth and Y is income. The trend produces a population distribution among wealthy nations, which contrasts what is observed among poorer nations. Underdeveloped countries from African countries, for example, display a population pyramid with a significantly huge base, a population distribution which contrasts the demographics seen in countries like Japan, Korea, and Singapore. In Japan, the segment occupied by younger generations has been dramatically shrinking since 1960s, resulting in society where the proportion of old people is significantly large. This demographic phenomenon alarms governments because a shrinking base of young people means a shrinking of workers and a diminishing source of finance to support pension systems enjoyed by retired citizens. Also in business cycle, the swings of ups and downs in GDP growth rate also reflects a pattern of economic phenomenon observed in many countries. It is the business cycle of growth and decline. Economic development measured in GDP growth rate does not progressively increase uninterrupted. It seems always to dip for some interval of time between it rises again to a new height, before it rises again to a new height. So see, even human populations can be seen a pattern, with a pattern. Human productivity. Human productivity in many organizations is observed to follow the 80 is to 20% rule. 20% of the members produce 80% of the organization's total output. For example, in a complete lineup of 15 players in a basketball team, 3 players make 80% of the team's total points in a game. In a sales force of 50 agents who made 1 million pesos total sales, 0.8 million pesos was brought in by 10 agents. The rest managed to bring only 0.2 million pesos. So we are still in the frequently observed patterns in nature and the world, but this is the last part. So in the figure, it shows the Philippine fertility rate versus the GDP growth rate. The plunge in Philippine GDP in 1985 was an exception in the national GDP growth rate, which in general has been progressively increasing for the past 3 decades. The sudden plunge was a result of economic and political uncertainties in the years 1983 to 1985. Among them are the difficult external debt payments, the assassination of Ninoy Aquino, and capital flight due to an unstable political environment. Data source World Bank. Productivity of people is also observed to follow pattern. This pattern is given a name 80 is to 20% rule, also called the law of vital few. This rule is a consequence of an observation that people working in an organization do not perform in equal measure in relation to productivity. Often, it is only 20% who produce 80% of the group's entire output. This observed in sports teams, in sales teams, in business, in creative endeavors, and also in the manner that student groups accomplish their groups projects. In a group of 5 students who work on a class project, chances are the project got finished and submitted only through the dedication of one member. Is that true? Maybe, because productivity is tilted in favor of the 20%, much of the rewards of productivity, measured in terms of income or wealth and power, also go to those who compose the 20%. The implication is easy to comprehend, but sends us reeling with discomfort. People in general are ill at ease thinking through the implication of this rule. To find out, let's proceed to the next slide. What it means in human organizations and societies are possibly inherently unequal in relation to wealth and power because differences in productivity have a consequent effect on their distribution. In addition, this inequality grows as organizations and societies become increasingly more complex. This phenomenon was first formally stated in economics by Vilfredo Pareto in 1896 as a consequence of his observations of land ownership in Italy. At that time, roughly 80% of all land in his home country was owned by only 20% of all families. The 80 is to 20% rule is known in economics as the Pareto Principle, and the resulting extremely uneven distribution of income and wealth in society is called Pareto Distribution. So I hope you see the difference between the Pareto Principle and the Pareto Distribution. The 80 is to 20% rule is also known as the law of the vital few, which in economics is stated as the Pareto Principle. It states that for many events, 80% of the consequences come from 20% of the causes. In most cases, the distribution of productivity and consequent effects of that productivity to specific segments of the population may not exactly equal the 80 to 20% ratio. But the underlying proposition stays the same, and it is thought-provoking. The law of the vital few resonates in the famous 80 over 20% rule and in the Pareto distribution describing the distribution of wealth in society. In so many productive or creative endeavors, only a tiny proportion of the group produces the significant part of the group's entire output. This has the result of skewing the distribution of wealth and power in favor of the few. Is extremely inequality in human societies among the laws of nature? Is this pattern wired into human relation? See the figure below. In this side, Pareto distribution and the 80 to 20% rule. The horizontal axis, proportion of the population of members of an organization and engaged in productive work or creative endeavors. Vertical axis, productivity measured in terms of the value of output in society or organization. The law of the vital few resonates in the famous 80 is to 20% rule and in this distribution describing the distribution of wealth in society. That's why you will ask, in the Philippines, only few people are that rich. In many countries, there are people who are rich, but most of the people are poor. So that's Pareto distribution. So it's also a pattern in nature, frequently observed pattern in nature and in our world. There are some events where 80 is to 20% rule and the Pareto Principle are observed. In conducting meetings, in a business or group meeting, 80% of the decisions are made in 20% of meeting time. In manufacturing, 80% of the company's revenue will be supplied by 20% of the company's products. In crimes, in law and order, a large percentage of crimes are committed by a small fraction of the total population. In sales force, in sales, 20% of the sales force brings in 80% of total sales. Exercising and training. In sports, 20% of the exercise and training routines contribute to 80% of total fitness. Group study or groups project. In group assignments and reports, so much of the finished output is done by one student. Computer crashes and errors. In computer programming, 80% of the crashes and errors in each system are eliminated by fixing the top 20% of the most reported bugs. Disaster prevention. 20% of the hazards are the direct causes of 80% of the injuries. Wealth distribution. 84% of the wealth created in the world in 2017 were to 1% of the world population. Oxfam.org. So that is all about what is mathematics and patterns.